Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Emina Soljanin. She will be speaking on quantum codes and correlations. Professor Emina is a distinguished professor of electrical and computer engineering at Rutgers. Before moving to Rutgers in January 2016, she was a distinguished member of technical staff for 21 years in the Mathematical Sciences Research Center of Bell Labs. Her interest and expertise are broad, currently spanning in distributed computing and quantum information science. She is an IEEE Fellow, an outstanding alumnus of Texas A&M School of Engineering, the 2011 Padovani Lecturer, and 2016 and 17 Distinguished Lecturer, and 2019 IEEE Information Theory Society President. In 2023, Emina received the IEEE Information Theory Aaron D. Wyner Distinguished Service Award and the Miss Urmila Agrawal Distinguished Visiting Chair Professorship at Indian Institute of Science. Over to you, Professor.
All right, so thank you very much for inviting me and for the introduction. I'm very happy to be here. All right, so I can see some familiar faces. This looks a little bit like magic with these cats and hats, etc. But actually, it's there is a couple of papers that we have. Let's see if this is working. Yeah. My student Michael Schleppi, our student collaborator, is actually an aspiring number theorist at the University of Toronto. And I had a paper that we submitted a couple of years ago and maybe appeared a few months after that. I think one of your professors, Professor Naveen Kaishap, was one of the guest editors for that journal. We also have funding for some of this, had funding for some of this work. Maybe we'll get some more. And also what makes me the most proud is that Michael got this very prestigious graduate research fellowship that is at the university level, actually is given by the National Science Foundation of the United States. And usually our university gets about 16 and 20, between 16 and 20. And last year we only got 4 because of various changes in funding research, and Michael got one of them, so I'm very happy about that. But things will get a little bit technical in the second part of the talk. I know that some of you have background in quantum coding, quantum error correction, and so that part is for you. But in the beginning, I'd like to just talk a little bit about codes in the light that you've probably never seen them before. So we are going to start with a game, and it's the end of the day, but still we maybe can make it interactive. And it's called the head color guessing game. So this is how it goes. How many people heard about head color guessing game? Okay, maybe not many or not at all. So what we have here in its simplest version is we have 3 players and a judge, and later we will generalize it. And judge, the players come in a room, like a few people came out in now, and the judge tosses a fair coin and decides whether he will put a gray or a red hat on this person who just came in. And these gray and red are Rutgers colors, but it will become zeros and ones for us. And so the players will have a chance to observe other people's hats, but not their own, right? So their task is to guess the color of their hat. So once when they had a chance to make these observations, they will offer a guess. And there is a winning condition, as in any game. So if someone has to speak. So it cannot be, but any player can either speak or pass. So it cannot be everyone is quiet. So and no one speaks and everyone says pass. That way is a certain way that the players will lose. So someone has to speak. But whoever speaks has to guess his color correctly, right? So so at first you look, so that the question is now, what is the maximal winning probability and how should these players play? They're not allowed, of course, I cannot say now, you know, Sakshi, what is my hair color? I mean, my head color, right? We can strategize in advance, but once we are in this room where the judge is, we just can guess our heads colors, and that's the only thing that's allowed. So it's tempting to say, well, you know, it's totally random. I cannot do anything but just randomly guess my head color. So what would be then, if each one of these three randomly guesses the head color, what would be the winning probability? Randomly guesses and decides to speak up. How?
It's all color possibilities are equally likely, and they just guess. So
yeah.
It's just one age that they all three have.
Exactly. So I guess something. I am right with probability half, and any other player is right with probability half. There are three players, or you can say there are 8 possible strings, and only one is there. So can they somehow do better than this?
I think first, fix an order. One of them can check whether the two hats are the same or not. And then have a fixed code for them to say that guess the hat color, but it's actually not the hat color, but just an indication of the parity.
I see.
Same or not.
Okay.
Then maybe the second person will say something about the information of the third one, because the person has access and sees them.
All right. So that reminded me of another head game where they can get sequentially.
So here what happens?
Here they have to speak up together, yes. So is there any, that is connected with complexity. So this type of games are connected with codes. You've heard that parity was mentioned, but also with complexity, especially this other one. Is there something that you can do better than 1/8? So not everyone has to speak, right? So you can say the first one, again, we can number them, and one of them, whichever, say the first will do the guessing, and the other two will pass, right? So that's half. So they will win with the probability half. Is that clear? Yeah. So now, let's look at this. So these are all these possible strings of length 3. And the strategy is going to be the following. A player offers a guess if he sees 2 identical colors. Otherwise, stay silent. So in this first case, when they all get either 3 identical colors, either 3 zeros or 3 ones, they will all speak. And they will all be wrong. But if the situation is 1 0 0 or 0 1 1, so the first one is the one that sees 2 identical colors, he will be the only one to speak. And he will guess opposite than what he saw, and he will be right. So 3/4 of the time, in all of these 6 cases, they will be right, but these other 2, they will not be. So this is 3/4, and I'll make some observations for coding theorists about optimality of this. You cannot do better with 3 players. So this is what they can do.
Silence strategy seems like out of the blue. In the sense that the assumption was that everyone has to speak. Or at least that's what they had.
All right. Let me see if this works, because we were having problems with when. So they can guess the color of their own hat or pass. Yeah. So, but they cannot all pass because someone has to speak. If all pass, that's a loss. Okay. So with this strategy, let me ask you one question which is going to be later important. If you look at only one player, like if you play for a long time, and sometimes, you know, I'm one of the players, right? And sometimes I'll speak, sometimes I'll pass. Am I going to be right when I speak? Half of the time, less than half of the time, more than half of the time? When I pass, it doesn't count. You cannot say what I'm thinking. So you actually, and we will show that in a more general, you cannot be right more than half because you don't have that information, right? So that's an information theoretic conclusion. The only thing you see has nothing to do with what's on your head. So you cannot. So what this strategy does is somehow concentrates the wrong guesses into two situations, into two strings. So with this strategy, their guesses are kind of moved into these two strings, wrong guesses, and the right ones are only one speaks. So this is not going to help you with individually. So can we extend this strategy to end players? And some of you may know this game. But what I want to do is make some observations that about what we just did. Players are given a random 3-bit string, and each one sees 2 bits. They based their guesses on this set that contains 3 zeros and 3 ones. So monochromatic strings, right? And then if the string belongs to this set, they will all speak. And they will all guess wrong. So out of all of 8, I put all wrong guesses into this set. And now, if S is not C, in C, at the most one player will speak, right? And it's at most one can see 2 others that are different colors. If it's not in C, one of them will have a different color. And that is the one that will see 2 others that have the same color. It cannot be 2. Or more, right? And the 5th condition, which a non-coding theorist would probably merge with the 4th, is that any other 3-bit string is only 1 bit flip away from those that are in C. This is the same C, just a typo. So at least one player will speak. And we said at most one, so exactly one will speak. And he will be right. And so for coding theorists, at most one will speak. What does that mean? So this set here is our code, repetition code. It's also Hamming code, right? And at most one will speak means that this code has distance 3, right? That it's not. And any bit string is 1 bit flip away from those that are in C. It means that C has a cover with its covering radius of 1 covers all code words. So we know that Hamming code is perfect. So that's an observation for a coding theorist. Then if you're a coding theorist, then you may know how to generalize this. So there is a generalization. Coding theorists can make sets. They're called Hamming codes. They're subsets of this vector space F2 to the n, right? These codes. And each player will get its coordinate number. So now he will not look whether by flipping his color he can make the string monochromatic, but he will say whether by choosing his color he will make the string monochromatic, but he will say, can I pick the color so that I make what I see together with my color a code word? So coding people, is that clear? Or can I pick my color so that with it I will make what I see and what I pick a member of that set C? Right. And if this set is sufficiently small, it has to be sufficiently large so that any string of length n is can be obtained from one of these by 1-bit flip. But you also want it to be small because you want to concentrate, to push everything to that set. That's wrong. Yes.
But for this particular game, all the possibilities of zeros and ones in the string are old words, right? Because the judge picks randomly.
Yes.
So your particular bit value being 0 or 1 is decided by the judge.
Yes.
And both 0 and 1 are possibilities. So both of them will pick code words, right?
So it will be one of the strings in this of n-bit strings. And I have put it with this notation because it gives me some algebraic structure, which I will need later. But all of them, it's true that all of them will be one of these strings. But I'm looking for a smaller set, like among those 8, right? If n is 3, I had 8 possibilities, and I looked for a set that has 3 zeros, 3 ones. Now I'm looking for something that can play that role. And coding theory is called that Hamming code. We'll show it later. Does that answer your question? Okay. And in order to prove that, you need to realize that these Hamming codes are perfect and use some covering arguments. Again, if these words sound non-familiar, this is just to say that some standard coding techniques can do this, right? Prove that this is optimal. So now I'm going to do a 2-step modified game and ask you a question. So you know those all or nothing shows, right? So you enter and the judge tells you this is how the game works, and that is what I just described. But you can either play that game, where if you have a large number of players, it's not too bad. Your probability of winning is n over n plus 1. Or you can commit to 2-step game. In the first step, you can do whatever you want to do, right? But you can play the original game. And in the second step, everyone has to speak. If you win in the first, you will. That's fine. But everyone has to speak. I mean, that doesn't count. In the second step, you. In the first step, you can play the old game, but you have committed to 2 steps. So if you win, you still have to play the second step. So in the second step, the rules change. Everyone has to speak and everyone has to be right. Otherwise, you lose. Would you choose the original game or this game?
First, there's no cost or penalty for guessing it wrong.
Exactly. No, but there is no cost. Just the odds are n by n plus. Exactly. And we said it's optimal. But if you commit to the second step, whether you were right or wrong, you still have to play it. So would you choose this second? Yeah.
Are you allowed to pass in the second step as well?
No, everyone has to speak up.
To pass is not allowed.
No, everyone has to. So in other words, what I'm asking you is how much information was revealed by the first person speaking up, in the first round.
So one more question. In the first round, you have to play the Hamming code-based strategy. You cannot deviate from that.
Exactly. But yes.
First round. So, I mean, you guess correctly only if you're having this response.
Exactly. So actually, I'm going to put.
The person speaks up, then I'm guessing that all the others can guess what is happening. Therefore,
Yeah. So yes. So we'll show that so it's the answer is, and I'll try to clarify a little more. Is it's good to play the 2-step game, and that is not that hard to see if you have these, because what happens is the following. if one speaks, and here, number one speaks, and it says, if it's in this case, he will say 1 and he will be right. So the others know that they have zeros. So they learned everything, right? If they all speak, right, they're all going to be wrong, so in the second step, they will just flip what they said. Is that part clear? So basically, whoever speaks will reveal by its position that he was the one that differs from the others, and it will tell how it differs. And so everyone will know. So how does that generalize? So this is what Professor Vijay said. We can see here the coding theory is called the standard array. So that set C, when you have 7 players, becomes something that I couldn't fit in the page, right? There are 16 of these words. And so if so this is the set C. So suppose that you are in a situation that you got this marked shaded row here. So the third player will speak. He will speak only here. Everyone else will speak, and he will also speak, or here. If he speaks here, everyone else knows that they are in this row. But from the properties of this code, which again may not be obvious if you didn't play with these objects, we know now that all information is revealed. So in this case, everything is. Another point that I was making is, does one player, is he now more right than, can he guess with a better probability than half? And the answer is no, he will speak either here or here, player number 3. Everywhere here he will be wrong, everywhere here will be right, everywhere here wrong, but these are all in 16. Everything else he will pass. So that is what is happening here. But what I wanted to make a point before I go to the quantum world, which has nothing to do with this game, is that codes can create correlations, right? We can base the games based on correlations. So there are other things that are going to be similar with quantum games, and that is that there is a challenger and cooperating players, and these players are distributed, they are non-local. The challenger chooses some math object at random, right? Here it was choosing 0 or 1. It reveals some information about the choice to each player. So to each player, it sees the rest, right? So something will be revealed in general. The players cannot communicate once the game begins, but they can devise a strategy before the game starts. So the optimal strategy and revealed information. So no strategy can change individual guessing rates. You cannot beat information theory. And the color configuration becomes known to everyone. So you will see that in quantum, this second thing is not going to be true in the example that we are going to cover. Yes?
Two-step strategy. After step 2, everyone guesses correctly.
Everyone has to offer a guess.
And there is a way by which they can all guess correctly.
Correct.
So in that case, the individual guess rate is 1, right?
Yes, after additional information is received. Correct.
So bullet, no strategy can change individual guessing rates because
In the single player game. Yes, that's actually great. Head color guessing game. The two-step is something I devised, but a head color guessing game is standard, except people didn't look at it in that light. I should make clear that these observations are for the standard head guessing game. Now, if more observation is revealed, as it is in the first round, then everything will be correct. Does that answer your question? Okay. So the optimal strategy correlates individual guesses. So why I'm talking about this? Well, one reason is things are going to get a little bit more technical here, maybe quite a bit more technical in the quantum case, but also because it has foundational importance, not only in quantum computing, but also in quantum mechanics. So in some time in the 30s, Einstein came up with, and Podolsky and Rosen, with some examples which allowed him to claim that quantum mechanics is either non-local or incomplete. And because there are no local, it cannot be non-locality in physics, it's incomplete, and therefore there are some hidden variables. Right? And for a long time, so this is mid-30s, until mid-60s or so, any example, game or whatever scenario that you could think of, you could explain by quantum mechanics, but you could also explain by hidden variables. So it was not doing anything right. And Einstein did not doubt quantum mechanics, it's just its interpretation is what he had a problem with. Long time ago, I read this book before even knowing about quantum computing, which was called Ghost in the Atom, and talks about various interpretations of quantum mechanics, and that's why this ghost is here. Right? So in the mid-60s, there was John Bell, who came up with some examples, and something also, another group of people that had something that we now know as CHSH game. And those examples were first to show that there are scenarios where you cannot explain things with hidden variables, but you can with quantum mechanics. So whatever classical hidden variable scenario you can think of, there is a difference between what quantum mechanics would indicate. And if there is that difference, then the idea, the realization was that we can build experiments. And if you build experiments and observe quantum mechanical effects, then really there is some kind of spooky action in the distance, what Einstein called it. Right? And first experiment was built by Alan Aspey in the, I think 84, in any case in the 80s. So lots of time passed. So these are things that are not hard to explain because they don't require, I don't know, functional analysis or whatever, some big machinery, but they're not easy to think of. So anyway, so 30s Einstein, 60s first examples, and then these are all roughly, and then in the 80s this first experiment. Now in 2015 there was a declaration that the last loophole in this type of experiments has been closed. Because when you make experiments, you're not really working with mathematical objects as we know them, but some more macro objects, and one can question whether this really is a good model for a qubit, etc. And so that was 2015. So in 2022, Nobel Prize for Physics was given to some of these people. Alan Aspey, who did the first experiment, one of the people who is still around, who is had one of these examples in the 60s, CHSH game, and the third person was one who generalized, who did some generalization, let's say. We can talk more about that if you're interested. So what we don't know today is how these things are generalizing in multiplayer systems, right? There is also, some of you may have heard about the property called monogamy of entanglement, which led people to believe that once you have 3 players, right, in quantum, everything falls into water, nothing works anymore, etc. So that is what we are trying to find. And these are distributed correlations that we would like to know what you can do with quantum, and what you can actually do maybe with doing some smart use of coding, like we just did in this set game. So it's foundational, but also you can make an argument that is important for distributed systems. And in fact, I'll show you later how some of these things start. Okay, so any questions so far? Okay, so I'm going to go to quantum, and bear with me if you're familiar with these things. I know that it's a very brief introduction, so I don't know people who are not into this how much they will get, but let me try. I taught a few tutorials. So there are 3 things you need to know before getting into quantum computing. And that is how is quantum information represented. We represented had colors with zeros and ones, and they became elements of Galois fields, etc. But what is here? What is mathematical representation? How do we process it? What are the gates there? Is it in a, we know there is a bit flip in classical communications. What is it in quantum? And then how is classical information extracted from quantum systems? Because that's what we are after. We want some answers. Yes, computer can do various things, but for us, but what are the answers? So what is a qubit? It's a quantum mechanical counterpart to a bit, and it's a unit norm column vector in C2. So people, may like your vector to be boldface or to have a little bar or little arrow on the top. In physics, they have this notation, which is called Dirac's notation, and two particular, and that denotes column vector, and two particular ones, something we call 0, which is vector 1, 0, and something we call 1, which is vector 0, 1, just regular little matrices, and they form a basis of C, and any other counterpart to a bit is a linear combination of these two. Physicists would be annoyed to hear linear combination because this is for them a superposition, and actually it is physically a superposition, and that's one of the things which makes quantum computing powerful. And the superposition makes it possible to compute things in parallel, exactly. But now, yes, you can compute things, on the entire domain, but how do you get the result? If we want to have several qubits, we don't just combine individual, but, and that is different than classical, but any vector in a C to the n place, actually C2, would be a valid state. So, for example, this vector, 0, 0, 1, 1, it's not a Kronecker product of any two single states. In fact, this is kind of a two register where we don't know how to describe some, well, we do, but it's not one of these vectors. How to describe what's in the first register, what's in the second. Right? So that is different. And so I said that one reason that quantum computing could be powerful is superposition. Another is what is called entanglement, and those are entangled states. So these vectors, we only can get one vector into another vector by applying a unitary matrix. So that is a postulate of quantum mechanics that says we cannot do anything else. These matrices can be Kronecker products of smaller matrices or not. And we often describe how they act by describing what they do to the basis vectors. If we have some basis vector in this large space of n qubits, and we want to act on that vector unitarily, it could be that that unitary matrix can be decomposed into Kronecker products of smaller ones. And for us, this is particularly important. Then by the properties of the Kronecker product, we have this identity is particularly important because we are looking into non-local games. So only a thing that the player can perform is something locally. And there are some of these unitary matrices. So a qubit is a vector in a two-dimensional space. I can act on it by applying 2 by 2 unitary matrix. Some are very important. One of these is this Hadamard matrix. There are some other matrices which we call Pauli. You may know it from your quantum work, or you may know it from some other mathematics work under a different name. There are also 2 qubit gates which are going to be important for us, and the most important one is the one we called controlled NOT, which takes 2 qubits. Here we describe how it acts on a basis vector. The first label X, it just passes as it is. The second one is flipped if the first one is 1. And that's why we are calling it control not. So flips only if the first one is 1. We can use Hadamard gate and the CNOT gate to generate entangled states. We cannot locally generate entangled states. Something has to be together to get entangled. One more thing to know, and that is how is classical information extracted for quantum. For this talk, there is a postulate in quantum mechanics that says how. For this talk, we will use measurements that are described by a set of matrices. These matrices are projective matrices, right? They're idempotent and Hermitian. And they're orthogonal to each other. That's property 2. And property 3 is that they form a resolution of the identity. So when I want, so this measuring apparatus is described by this set of matrices. When I want to measure some set psi, what I get out is a projection of that state, normalized again to preserve the unit norm of the vector. So this is what I get out. I don't get that out for sure. I can get that for any x with a particular probability. So the only possible results, the only clicks that can be made here are one of these x's. And what I get out as a vector, people say, you may have heard things like collapse of a wave function, and then some other people saying nothing collapses, or projection, or things like that. But this measurement is not something that is reversible, whereas multiplication by unitary matrix is. Okay. And so now we have all these tools. If you know them, you knew them before I said that. If you don't know them, I don't know how much I told you. But anyway, this is what it is. And now I can introduce something called a Coset guessing game. I'll give you a little bit of history of this game a little bit later, because it will be easier to tell it once when we know, once we define certain things. So over here, we have, this is very high level. Alice draws 3 mathematical objects. And based on them, she will prepare a multi-qubit state. I'll tell you later what these mathematical objects are. But in any case, there is a mouse, bear, and a cat here. And then she will form some 2n qubit states, so some qubit state which has even number of qubits, and send half of the qubits to Bob and half to Charlie. She will reveal the mouse, the identity of the mouse. So once when she sends that, she will say, this is what the mouse was. And she will ask Bob to make a guess about the bear, and Charlie to make a guess about the cat. These are not, they're chosen independently, but the qubits are built based on all 3. Right? So this qubit state, so she randomly draws these objects, but the qubit state is built based on all 3. So by revealing one of the objects, she also will reveal something about the qubit state. So let's see now what this really is. So now let's forget about cats and bears and mice, but what I need as ingredients is a subspace of f2 to the n. This is classical subspace. And this G and K will denote the set of all these subspaces of dimension K of space of f2 to the n. And then now there will be, this object is called subspace state. For those of you who are familiar with CSS codes, it might be something that you will recognize. Right? So now forget about K. we have a generalization to K, but the original game came with all this choosing an n-dimensional subspace of this F2 to the n. And I'll give you some examples later. Uniformly at random. And then also chooses X and Z, chooses also two strings of length n. So subspace and these two strings of length n. And forms this state. Right? This is called the coset state. Right? And she sends, so this now has 2 to the n qubits. She will send the first n qubits to Bob and the second to Charlie. In the original game, Bob and Charlie can request some transformation of that state before Alice sends, but not in this talk. This optimality for this is still an open problem. We have some numerical results if that's something that you like and would like to talk about. Then she will reveal this mouse. She will reveal the choice of W. I didn't have to put here the cats. She will reveal which subspace she took, right? But no, so if you were having a code, this is like she will choose a code, but she will not tell you X and Z cosets in X and Z, sigma Z and sigma X errors, right? And so here is an example. So there are 3 one-dimensional subspace of F2, so just 2 qubits, just 2 qubits. So 3 one-dimensional subspaces. Each one has to contain 0, 0, it's a subspace. And then the first one contains 0, 1, the second one 1, 0, and the third one 1, 1. And I am out of vectors, right, with when n is 2. When n is 2, what are my strings of length 2? 0, 0, 0, 1, 1, 0, and 1, 1. 0, 0 has to be in every subspace. 1, 0, and 0, 1, and 1, 1 are the other vector. So this is the... So now, what are the coset states? There are actually many more of them, but quantum mechanically they're equivalent to this. So this is if she chooses the first one, this is the upper index. The upper index tells you that it goes here. This upper index, that these are derived from this, and this upper index, they are derived from this one here. You can derive that these are the states that she has. Plus is 0 plus 1 over square root of 2. It appeared in one of these earlier slides, and you caught it. So now, Bob can really, in this case, so coding guy, I mean quantum people, how can Bob and Charlie figure out the coset, right? They need to figure out, so Alice will tell them what W1 is. They need to figure out if what the cosets were chosen, if it's 0, 0, 0, 0, or 0, 0, 0, 1, or 1, 0. They have to figure out these. Bob has to figure out the first one, Charlie the second one. I don't know if any... So Bob can essentially only measure in the computational basis, right? And he will get, if he gets 1, he will know it's 1, 0. If he gets 0, he will get 0, 0. So he can guess completely correctly. And Charlie can measure in Hadamard basis. If he gets plus, he will know it's 0, 0. If he gets minus, he will know it's 0, 1. So they completely can resolve this by individually measuring their qubits. So the qubit that Charlie got, that Bob got, was the first qubit. The qubit that Charlie got was the second qubit. And they're in such states that they really correspond completely to this. So they can just measure and figure it out, so they're fine. Now, it's amazing how this one example actually tells about various situations that can appear. This one I will not get into because it involves entanglement, and that's only if people are interested in reading the paper. But this other one, if you notice now, these two things are flipped. So Bob got information that Charlie needs, and Charlie got the information that Bob needs. So now forget about quantum, just a general question. I have some information, either I or Sakshi can get either 0 or 1. And by looking into quantum looking here, I can definitely say what she has, and she can definitely say what I have. But that's not what we are asked to guess. So one thing that I can do is say, well, you know, these are unrelated things. Whatever I have here has nothing to do with what she has there. And therefore, I can just randomly guess. And she can do the same. And she will be right half of the times, I will be right half of the times, and our joint probability would be 1/4. Can we do better? Completely classical question. So one thing I can do is just pretend that what I got is information that is relevant to me, although I know this has nothing to do with me, it's actually information. So this is what I'm going to declare. I'm really going to look into it, perform the measurement which I need in the quantum, and declare this is what I have. Although I know it's that only with the probability half. This is what Sakshi has. And she will do the same with her information, right? She will observe it and declare whatever she sees that that's her best guess. Again, it's not going to bias anything individually, but it's going to do something jointly for us. So if you think a little bit about that, you will see that we are either both right or both wrong. So this possession of these things that are not relevant to us did not do anything for us individually, but it allowed us to correlate our answers. So we are either both right or both wrong, and therefore there are two options, both right, both wrong, so therefore we are both right with probability half. So we are successful with probability half as opposed to probability 1/4. And here's something that you will not be able to read, but the slides are available. These subset states and coset states, they first appeared in the CSS codes. And there were there was some work at that time about hidden subgroups, etc. But almost 20 years later, in the computer science community, Aronson and Cristiano came up with this subspace state, which is as a cryptographic object in connection with quantum money. And anyway, there were some other things there. And then we were reading this paper we were interested in monogamy, and there were this paper actually, subspace coset monogamy, and there was something conjectured before which they managed to prove, but they got some exponential bound, which was good for whatever cryptographic protocol they wanted to show works. But for a coding theorist, you want to know what's actually happening. How are these things? So that's what we worked into. And so there is 10-15 minutes left for my talk, so I'm not going to now bother you with the detail of this, but I'm just going to tell you what is involved. So again, there are Bob and Charlie get each n qubits out of a 2n qubit state. 2n qubit state is formed based on choosing an n-dimensional subspace and 2 cosets. So if you had a CSS code, it would be like choosing a code and z errors and x errors. So in that sense, it's none of these previous papers connected this with codes. So, so Bob can measure his n qubit and has to guess S. Charlie can measure his n qubits and has to guess Z. And my students often give me cooking examples. And one of the students who was trying to tell me how she understood entanglement, she said, you know, this is like a marble cake. You have vanilla and chocolate, and you cannot really separate them. And then when I was thinking about this, what's it called, this problem, I said, yeah, like marble cake, then you cut it in half, give half to Bob, half to Charlie, and you're asking Bob to figure out all vanilla, and you're asking Charlie to figure out all chocolate. And it looks impossible. And actually, it is. It's totally random. So what, I want to just tell you how we, what we did. So the previous, so this is just description of the game. Let's see. Right. So I said there were people who were looking into this, and whatever, they didn't claim any optimality. What they found was sufficient to a practical problem, well, practical, whatever quantum is, a problem they wanted to solve. And so what we did is derived an upper bound and then showed how to achieve it. And it's actually very similar to this 2-qubit example, where I was saying that Bob and Charlie are either both right or both wrong, but they get no information revealed. So what about the bound? The bound on the probability uses, I'm not going to get into that, but uses mathematics that follows from some operators inequalities. Why operators inequalities? Because your measurements are these matrices, you use matrices. So this is this first. And then to show that this is order of theta 1 over 2 to the n is some binomial and Gaussian binomial coefficients inequality. Why Gaussian binomial? Because you're talking about subspaces. So what we showed that actually they cannot win, or actually marginals of this probability cannot be better than asymptotically 1 over 2 to the n on average, because otherwise there are cases, as the first case in the example, that they can be completely right. But they cannot on average, expectation of this probability cannot be better than 1 over 2 to the n. But now I am asked to guess a coset of an n-dimensional space. N-dimensional space in a 2-dimensional, which is a subspace of a 2-dimensional, 2n-dimensional space. And so there are 2 to the n possibilities. So I'm not doing anything better than random. So in spite of having these n qubits, I'm not getting anything better than random. That is not, oh, of course, there is an information theoretic bound like in the head game. It's not, because here you got some information, right? So how do you show that you cannot do better? However, the way it's split allows you to correlate these two. So how did we figure out these correlations? That was helpful to think about the CSS codes. So for those of you who know that, right, if you look at the entire space be your code C1 and this W be your code C2, then your coset space is an error space. So your subspace W state is an image of an all zero state. So all zero state is encoded into this W. Once when you choose cosets, these are like your errors. This is how we describe errors in the coset, in the subspace and coset, in the CSS codes, sorry, or in quantum in general. And what we usually do is we pick up the minimum weight coset representatives for decoding. What we will do here is actually what we managed to do is find how to map all zero state, find the network N that maps, and this consists only of C-naughts and Hadamard's. And if we choose the supports of these cosets to be disjoint, then then these commutes, we can show that, and the state that we get is network times x plus z. So this network is a circuit that I may not be able to undo because I don't have the entire 2n, but in many situations I will be able to undo it. So what is it? Again, I'm not going to go through all of this here, but what I want to tell you is the following. So this is I think when I was giving some short talk impromptu, I found an example of the standard array in Wikipedia, this 5.2 code. So anyway, so this is a code in the first line, and this is these lines here are cosets and columns are spheres. So usually we take the minimum weight 1 and we go with the minimum weights until we run out of minimum weights and then have to take minimum weight 2 and so on. Here we are going to get cosets with particular support. And that is, which support is based on what the generator matrix of the code is. So I have basically highlighted here to just show that it's possible. It's not, the representatives are not here, they're somewhere else. So anyway, these are some tricks that we used. Of course, I swept a lot under the carpet here, but it gets really to be very technical. And so now, I said that we had these, this is the theorem, that we can undo some of these things locally, depending on what the generator matrix of the code is, or what this A is, describes this W, but may not be. And again, what happens here is, if we are able to undo things locally, we can get this information in the clear, but it may not be on the side where we want it. But then again, you know, we just said that we can live with that, right? We can ensure that there is correlation. If we cannot do it locally, that means there are entanglements between Bob and Charlie. That takes much more work. But nevertheless, the point is that that Bob and Charlie cannot do anything about individual error rates, which is not the information theoretic bound, is something that needed a proof. They can make their guesses entirely correlated. This one describes what it is in this particular case. And that is what it buys you. So the shared quantum state only correlates individual guesses, right? And the optimal strategy turns quantum correlation into classical for large number of states and does not improve into individual rates of correct guessing. And what else can one do here is, of course, Y2n and n, you can generalize it, and we did a little bit on that work. You can take this W to be some code. And most importantly, related to the general problem is, what if Bob and Charlie say, okay, before you tell me W, I want you to transform your 2n qubits by some channel phi. There is some legal quantum transformation. And then send me the qubits. Does that buy anything? It turns out, based on the numerics that we did, that in some small cases that it does, but we don't know how that works, right? We are now looking into some other types of games that concern monogamy, but there are many. I don't have a big group, right? I have one student who does quantum, and one who does distributed computing, and one who does regular coding. So, and one of them is masters, so that's very limited. So there are many unanswered questions here. I try to keep not more than an hour with this. So that's all I had to say.
Thank you very much, Professor, for delivering an interesting talk. Are there any questions from audience?
I just wanted to understand a little bit more about the, you had a result where you mentioned the probability of win lower bound, and then you could achieve it, upper bound, and you could achieve it as n becomes larger, asymptotically. Can you tell a little bit about, why do you need larger and larger n, and what does more qubits, what does that give you that enables you to get to the bound?
Yeah, thanks. So, so even in the small case, some of these situations are exemplified, right? One is the first one, the first column, where both Bob and Charlie can guess correctly. The second one is they cannot do anything better than random, but they can correlate. Although there is a classical correlation here, which takes some thinking to see. And then here, it looks even more hopeless. And that is, but it turns out that if they do some kind of measurement in the Y basis, so that's one basis we almost never use, right? That they can correlate their results even here. So, so even the small examples show that. So here would be, they would, with the one, they would be right with probability 1, and then together probability half, and together probability half. That would together give me 2 divided by 3, because with 1/3, I would get 2 over 3. So I am not going to get better with more n, but I may get worse. So instead of 2 over 3, I will have 1 over 2 to the n. N here is 2, so it would be, 2n is 2, so it would be 1/2, but I'm getting here better, I'm getting 2/3. So these advantages are going to disappear. So the larger n is not going to make me better, but it will not go below 1 over 2 to the n, which is a random guess. I am not sure. You had a second part of the question. Yeah, okay, sorry.
Any more questions?
So I just, if there are no questions, I just wanted to, because many people here are working on CSS codes, and so I asked many people if they've seen these kind of networks before, but if someone has, it would be nice for us to know, because we had to derive that I can get any W. These J and I are sets based on they're defined here, they are based on the generator matrix of C2, let's say. And so I can get 0 state and get any W by using these C0 and HIs in this way. So if you've seen that maybe in some encoding of CSS codes, let me know. I did ask quite a few people, but who knows? So that would be interesting for me to find out from you. And then if I put them, I have to put the generator matrix in the reduced row echelon form, and then form these sets. One is where the pivots are, and the other is the pairs of sets where Aij is 1. But the first index is pivot, the other one is the complement of the pivot. But I only care about the pairs when Aij is 1. So that was something that, and that allowed us to prove, where was the statement? Yeah, that proves this, but then also allowed us to show that this commutativity, there was somewhere earlier. I'm not sure where it is now. But in any case, that was, if you've seen anything of that sort. Okay, I'm here for, well, the last week of my stay is mostly holidays, so this week and next week are good if you like to talk. I already talked with some students, postdocs. There is the other line of work we are doing these days is some one-step majority logical coding of Reed-Muller codes. And then we are also looking into some dynamics of quantum error correction, which is more queuing theory than coding theory.
So we have arranged refreshments at Coffee Hut. Please continue your conversations there. Thank you all for attending and have a great evening.